Hey all dear friends, this is Prajesh Chaudhary of Quantum Group. In this video, I am taking a question from International Distributed Physics Olympiad 2020. What is International Distributed Physics Olympiad? Due to COVID pandemic in 2020, IPHO, International Physics Olympiad, could not take place. So instead, remotely alternative IPHO, named as a International Distributed Olympiad, took place. So here is a very good question of electrostatics from that IDPHO. Normally, the question I take from IPHO or INPHO, they are those type of question which have relevance for the IIT-JEE. So that is that kind of question. So let me read the question first and then I'll explain how we can do that. So here is the question. A narrow straight channel passes through the center of a fixed cube with a side A. The cube is uniformly charged. The charge density is rho. The distance from the cube center to the point of intersection of the channel in phase is L. In the channel, there is a particle of mass m and charge q. Find the period of small oscillation of the particle near the center. The gravitational interaction of the particle and the cube can be neglected. The cube and particle are oppositely charged. So basically, there is a uniformly charged cube of uniform charge density rho, and a tunnel is made through the center, and the charged particle having charge, which the sign of that charged particle is opposite to the charge of the cube, is released near the center, and it start oscillating, and we have to find the time period of that oscillation. So basically, for that we need to find the electric field near center. That is the main task, and once we get the electric field near center, we can immediately apply the m is equal to f naught, and then we can get a is equal to minus something into x, and then we can get the time period. So main task is how to find the electric field near the center of a uniformly charged cube. Normally we do not encounter this type of question because through Gauss law we cannot solve this question. So there is a very interesting trick that will be used to get this answer. But what is more interesting, that the result is actually the same as that of a uniformly charged sphere. But there is one difference, that while that result validates at all points inside the sphere, and that result here is valid only for the points very close to the center. So let's proceed to get the answer. Before we proceed to find the electric field near the center of the uniformly charged cube, and we need to get an allied concept. So let me do that thing, and that result will be used to get the electric field near the center of the charge cube. So what is that alternative problem? So what I want to find first, electric field at a point on the axis of a uniformly charged square plate at a distance equal to half of the edge length from the center, and this result will use to get the electric field at near center of the cube. So suppose I have this cube, this is square plate, it has some thickness also. This square plate right now I have just shown of uniform charge density rho, and obviously it will have some thickness also, so there will be some volume charge density also. This side is A, and this is a center, and this is a line perpendicular to the plane and passing through a center, and this distance is equal to the A by 2 from the center. A is the side. So what we have to find? We have to find the electric field here, and to do that, what we can do, let me place a charge here, Q. Charge is just a tool for me. So what we'll do, we'll find the force because of this plate on this charge. Before that, let me assume that this point charge is 1 and this plate is 2. So force on 1 because of the plate is, say, F12, and the force on plate because of the charge would be F21, and obviously they are equal and opposite from the Newton's third law. So F12 is equal to F21. So if this F12 is the force by the plate on the charge, and if we place charge Q is there, charge q is there. So if the electric field at P because of the plate is say E, then obviously E is equal to F12 divided by Q. And obviously F12 is equal to F21, so that we can also write F21 by Q. And now basically I am going to calculate the F21 first. So for that, let's go to the next page. So again the same plate, but right now in this diagram I've shown the thickness also. The volume charge density is rho and the thickness is T and the surface charge density is sigma. So obviously this sigma is equal to rho into T if the total charge is Q. So sigma is equal to Q by area, and the rho is equal to Q divided by A into T. So just put that thing value of the sigma, so we'll get sigma is equal to rho into T. So now what I want to find, I want to find the flux because of this charge Q passing through this plate. So for that, what you can do, just try to think of a cube. A cube whose at the center of that cube this charge Q is placed. So suppose if I construct a cube of side A and this plate is one of the face of that cube, so then clearly this charge Q would be at the center of that cube because the distance is A by 2. So because of this charge Q, the total flux passing through all the 6 surfaces of that cube would be Q by epsilon naught. And for that charge and that cube, this charge is symmetric with respect to that cube. So the flux through all the faces would be equal. So through each face, the flux crossing would be Q by 6 epsilon naught. So here, that is that kind of situation. The flux because of this charge Q through this plate would be Q by 6 epsilon naught. That is one thing. So flux crossing through a square plate due to charge Q, that is a phi is equal to Q by 6 epsilon naught. Now what I want to do, I want to take some little part here on this surface. Suppose I have taken a small area ds, and obviously the direction of ds is the downward direction, so that is a ds vector. And electric field ds, obviously that is a very small area. So electric field because of this point charge through this point is a E vector. And now suppose this angle is theta. So if I want to find the flux through this part ds, and that flux would be how much d phi, that is the E dot ds. Electric field and ds vector are making angle theta with each other, so E dot ds is equal to E into ds into cos theta, that is E cos theta into ds. So total flux through this whole plate would be the integration of this d phi, so that would be E cos theta ds. And now suppose the charge on this little part is say dq. So this charge would be how much? That charge dq would be sigma into ds. Sigma into ds. The charge on this area ds is dq, that is a sigma into ds. And now on this charge dq, this charge dq is placed at the electric field E, so there will be some force on this charge. So that force is say df, and because this is because of 1 on plate 2, so I will call that df21. So force on this little charge dq because of this charge, electric field is E, the charge is dq. So this df21 is equal to dq into that local electric field here. So df21 is a dq into E, and dq will write sigma into ds, and that is sigma E ds. The component of this dq1 normal to the plate. Once again I have shown this, this is the front view of this plate, it would look like that, and that is that element. This is d21, this theta, and this is the component of that force df21 perpendicular to the plate. So obviously this df21 perpendicular would be df21 cos theta. df21 cos theta. So all and the total force on this plate because of this charge due to symmetry would be in this direction. So this F21 is the net force. So if here and there I take so many ds, suppose I take some ds here, the force would be here. I take some ds, the force would be here. I take some ds, the force would be here. The vector sum of all these forces is F21. And for these F21, if I take the component of d F21, one component would be here and one component would be here. These all components parallel to the plate will get cancelled. So basically the F21 perpendicular component will get added up and that will give me F21. So F21 is the integration of dF21 perpendicular. Now I will write this dF21 perpendicular. So that is what dF21 cos theta. And dF21 is equal to sigma EDS. So put it here, sigma EDS. So sigma EDS cos theta, some arrangements. Sigma is constant, let me take it outside. So inside E cos theta ds. And integration of E cos theta ds has to be carried out on this whole plate. And that integration is a total flux crossing through this plate. So F21 is sigma into phi, and that is a direct result. So we got this sigma into phi is the net force F21. So F21 sigma phi, and we can write sigma in terms of the volume, charge density and the thickness of the plate. So sigma is equal to rho into T, and rho into T I will write, and this phi from here is Q divided by 6 epsilon naught. So overall we got sigma rho T Q by 6 epsilon. So the main task is done. And now we can get that electric field here. Once again, the previous diagram, this was the diagram. So electric field, because of this plate at this point, to get the electric field, we put a point charge here, and that point charge experiences the force F21. Then the electric field is F12 divided by Q, and F12 is basically F21. So E is equal to F12 by Q, that is F21 by Q, and we just got F21, that was a rho T Q by 6 epsilon naught and divide by Q. So the electric field at this point is rho T divided by 6 epsilon. Remember, in this result there is a no term of the dimension of the plate, but this result is only valid at a point on the axis of the square plate and at a distance that is equal to the half of the side length. So that is one. Now let's go to the original picture. That was the. So now we want to find the electric field near center inside a uniformly charged cube. With integration can't be possible. With Gauss law we can't do. So there is a little trick and some very fine approximation. So this is a cube. So let me take my coordinate system. This is a cube of side A. Now let me take my coordinate system at the center of this cube. So at the center I've taken my origin. This is x-axis, this is y-axis, this is z-axis. So and now let me take a point P inside. The coordinate of this point is say x, y, z, and this x, y and z each themselves are very small compared to the sorry, side of the cube. Mean x is very small compared to A, y is very small compared to A, and z is also very small compared to A. So in other words, this point is very close to origin. So to get this picture more clear, let me draw a cuboid of size x, y, z. The origin of this cuboid is at the origin of the coordinate. So this is, if this is x, so this length is x, this is y, and this is z. Now what we want to do, I want to make few cuts on this cube. So first I want to cut it like that, this way. Make a cut like this. So first I am cutting this way. So this length is 2x. And so obviously this length is a minus 2x, and then 2 more cuts, and now I am cutting like that, like this. Then one cut I have done like that. Now I am cutting like this. So let me cut this, and so this is 2i. So I have cut like that. This is 2i, and this is a minus 2i. Total length is a. And then also along the z direction we want to cut, and let me cut like that. So from here one more cut I want. So this is 2z and this is a minus 2z. So basically now with these cuts, this whole cube is cut into basically 4 parts. One cuboid, this is a cuboid of dimension a minus 2x, a minus 2i, a minus 2z, and this one square, one plate, this plate, and this plate. So because this z is very x, y, z are very small, so if we consider this plate and this plate, so this term would be the common term, so that will become 2 times. And on this plate and this plate, this term will also come twice, but that thing we can neglect. Why we can neglect? Because x, y, z are very small. So basically on cutting like that, we have divided this cube into 3 parts. One is this cuboid, and this I will say now, this I am including on this square plate, the square plate of side A and thickness 2x. This square plate of again this side A and the thickness 2i, and this square plate of side again A and thickness 2z. And now let's see one interesting thing. Suppose if I take this length and I want to see how this P fares, the location of this point is with respect to these plates or with respect to these cuboids. Suppose this is that whole edge A, and this is the midpoint of that edge. Obviously along, if I take that edge along x-axis, so that is the origin. This length is a by 2, this length is a by 2. So if I go to at a distance x from this O, so this will be how much? A by 2 minus x. So, and then if I go from here, a by 2 minus x, so the remaining distance, this distance, how much? That is a by 2 minus x plus a by 2 minus x is a minus 2x, so that will be 2x. So this is 2x. And now see, so this point, for this part of the length a minus 2x, this point which is at a distance x from this is the equidistant. So what does that mean? That for this cuboid, I am just explaining for the x direction. Same logic can be applied for the y direction and z direction. So for this cuboid of dimension a minus 2x, a minus 2i and a minus 2z, the selected point is exactly at the center. So that is one thing. So now let's go to next page and let me repeat the thing what I have told. So I told you that the cube can be thought of made of a cuboid of size a minus 2x into a minus 2i and a minus 2z, and this point P, here I want to find the electric field. At this point P is exactly at the center of that cuboid. And then there are 3 plates, 3 square plate. This is a 1 square plate. I'll repeat that I am including this part in this also, that I can approximate because x, y, z are very small. So the contribution, if I add or delete a very small part, that will not significantly affect my calculation. So there are 3 square plate. This is 1 square plate of side A and thickness 2x. This is another square plate of side A and thickness 2i, and this is another square plate of side A and thickness 2z. So because of all these three, we will find the electric field at this. Because of all these three plates and because of this cuboid, we will find the electric field at P. So clearly, first of all, electric field because of the cuboid part at the point P is 0, because that is exactly at the center. So it's only up to the find the electric field because of these three square plates. And you can take any, let me take this square plate along the x direction, this square plate. This is very small. So this point is approximately a by 2. This point is very close to the center. So basically, if I take this square plate of side A, so this is at a distance a by 2 from the center of that plate approximately. So the same result that we started derive in the initially, I will apply for this plate. For the electric field at P. Similarly, the similar result will be applied for the electric field because of this plate and this plate. So, electric field at P because of this square plate. This square plate is of side A and thickness 2x. So, because of this plate, electric field will be along x direction. Because of this plate, electric field will be along y direction, and because of this plate, electric field will be along z direction. So all the three plates will make electric field. So because of this plate, electric field was rho into T. T is the thickness into sorry, the electric field was rho T by 6 epsilon naught. So because of this plate, the electric field here is the rho, the thickness is 2x, divided by 6 epsilon, direction is towards the x-axis. Because of this plate, electric field is a rho into thickness 2i, divided by 6 epsilon naught j cap, and similarly because of this plate, electric field is rho into 2z by 6 epsilon naught k cap. So we can simplify and get that electric field is rho by 3 epsilon naught xi cap plus y cap j cap plus zk cap. So this is, suppose if this position vector of this point P with respect to origin, the coordinate of this point is x, y, z. So position vector of this point is basically xi cap plus yj cap plus zk cap. Let me call that r vector. So electric field here is at a radial away direction, that is a rho vector r by 3 epsilon. You see, this result is exactly the same because of the electric field due to uniformly charged sphere. That is a rho r vector by 3 epsilon inside it. But that result is valid for the whole sphere at all points, but this result is valid only for the points very close to the center. So we've got this result. Now we can get the cubic oscillation. So now let's go to next page. So here a tunnel is made inside that cube. That tunnel passes through the center, and we can take any point here, this point P, that is a very close to the center at a distance small r. So here the electric field is in the radial away direction like that, and the magnitude of that electric field is rho r by 3 epsilon naught. So this rho r by 3. If I put some charge here, if I want to make it oscillate, so obviously the force should be restoring towards the center of the force, towards the origin. So the charge should be negative, and that was given. So suppose the charge is say minus q. So charge is minus q, or minus q charge is placed here. So it will experience a force towards the center. So that force would be a minus q into E. So like that, and apply the second equation, Newton's second law, ma is equal to f naught. So a is the double derivative of that position r. So mr double dot is equal to f naught, and that f naught is a minus q into electric field. Just put the value of this electric field here. So that is a minus q rho r by 3 epsilon naught. So take m here. So this r double dot is a minus rho Q divided by 3 epsilon naught m into R. So this is the equation of the simple harmonic motion. Acceleration is directly proportional to that R and opposite to that. And that proportionality constant is the angular frequency square of the angular frequency. So this is omega square. So omega is square root of q rho divided by 3 epsilon time. So time period is the 2 pi by omega. So time period comes out to be 2 pi square root of 3 epsilon m divided by q rho. So that is this question. So what is the takeaway message from this question? That if some question comes in JEE for the Q, and remember one thing, that in JEE I will make a video and I will show that many questions have come in JEE Advanced. Few questions were directly the similar question from IPHO or INPHO, and few some modifications like a chimney problem. Once it had come in the Olympiad, so it had come the last year. So some modification of this kind may come. So nowadays the JEE is looking for some type of question which are usually not taught in the classroom. So that is a very good question, and the takeaway message that what is the electric field because of a uniformly charged cube near center, and that is the same as the electric field due to uniformly charged sphere. Thank you.